All right, lastly, we have the most difficult kind of linear, non-homogeneous, first-degree recurrence relation. And that's when our a value is not equal to 1, and we have some sort of linear function here. On any IB exam, I'm sure that they would guide you through this solution. So this is not a process that you need to memorize, but it's worth explaining anyhow. So we know that this is going to become u sub n equals, a to the n, a to the n, goodness, times u0, or a to the n minus 1 times u1, depending on your initial conditions, plus the sum from 0 to n minus 1 of a to the k, and then we know our function, times b plus c to the n minus k. But if we don't know the value, even if we know the value of a, this is something that could be really hard for us to figure out explicitly. So what we want to do instead is break our initial condition, our initial scenario up into simpler scenarios. And we do that by creating an auxiliary equation. And we'll look at this more when we get into second degree. But in the first degree, it would be to say, imagine that we had some sort of simpler v sub n equals a times v to the n minus 1. Well, we know that this has a solution of a to the n times k. Or we could say instead of k, u sub 0 or u sub 1, depending again how it was defined initially. But changing this part, which again, this is also a constant as well, this will depend on our value of n, but changing this into this means that we've modified all of these as well. So our new equation is going to have a to the n times k plus, we know that when we had our simpler version of our linear equation, we ended up with some an plus b. And actually this came, if you remember, an plus b. It was similar to this, where we ended up rearranging things to have new constants. So in this case, we're rearranging as well. We've changed this, which means that this must have changed as well. And again, any IB problem is going to guide you through this process. We still have 3 constants that we don't know. So we've got our k, our a, and our b, and we're going to use our initial conditions to help us find those. And so let's look at some examples so that we see how this works. All right, so here's our recurrence relation. Again, our a value is something other than 1, and we've got a linear expression at the end. We're given a u sub 0 value. So the corresponding homogeneous equation, our auxiliary equation, is v sub n equals 2v to the n minus 1. Well, that's going to be the same as 2 to the n times some k value. And we don't have initial values for v sub n. Our initial values are u values, which is why we're just going to call this constant k. All right. Determine the values of a and b in p sub n equals an plus b. So that's this second part here, but also knowing that p sub n is a solution for the recurrence relation given. All right, so let's think about what that means. So we've got p sub n is equal to some an plus b, but also p sub n is a solution to our recurrence relation, so 2 p sub n minus 1 plus n plus 1. We also know from this side that p sub n minus 1 is a times n minus 1 plus b. So now I can equate my p sub n to p sub n, substituting in for p sub n minus 1. So an plus b, replacing this pn with an plus b, equals 2a n minus 1 plus b plus n plus 1. So substituting in for my p sub n. And now I want to make these two sides look the same. So I want to have some sort of constant multiplied by n, and then just a constant. So I'm going to have my n values are going to be 2a plus 1. And then my constant values are going to be 2b minus 2 plus 1 is minus 1. Okay, this gives me oh, sorry, this isn't correct. This isn't minus 2, this is minus 2a. So negative 2a plus 2b plus 1 is the constant term. That means that I can set up a system of equations to solve. So I know that a must be equal to 2a plus 1, looking at the coefficients of n. That implies that a is negative 1. Knowing a is negative 1, I also know that negative 2, negative 1 plus 2b plus 1 is equal to b. And then solving this, I could find this is going to be 2 plus 1 is 3. That implies that b is negative 3. So putting all of this together, so we've solved this solution. Now we can write down the solution of our recurrence relation. So I'm going to come do that over here. We'll have that u sub n is equal to k times 2 to the n minus n minus 3. So negative an plus b. Here's my an plus b. I know that u sub 0 I was given. Now I'm going to use my u sub 0 is negative 1. So negative 1, k times 2 to the 0 is 1, minus 0 minus 3. That must mean that k is 2. Putting that together, I would end up with a u sub n value. Okay, so now u sub n, 2 to the n plus 1, minus n minus 3. And again, you're going to be guided through scenarios like this. But based on what we've just done, we can repeat it ourselves using these same ideas. And I will do that in the next video.